In the recording. So everybody, welcome to our Introduction to Networks meeting. I hope last week's meeting where we walked through the setup and configuration of a switch was useful for you. I do want everyone to know that I graded a great number of the assignments. Actually, everything that was turned in yesterday, I got them graded. And one of the things I'm noticing is some of you are turning in assignments for labs, but there's no corresponding net labs. Please be aware that in net labs, I've got to see that you actually did the lab in NetLabs to give you credit for a lab that's being turned in. Also be aware that in NetLabs, one of the neat things about it is that anytime that you do a lab in NetLabs, I can actually see everything that you've typed. So you really don't have to save the configs or anything of that nature. Oh, wrong one. In fact, if I go back and look at the lab that I did last week, there's my lab, should be right here. So you'll see basic in device switch configuration. You should be able to see under the devices, I can actually see the session logs, and I can see where I completed or did this lab last week as I was in class with y'all. So, or actually on this one, you can see that I didn't do anything. I just logged into this one. So it must be a different one of my reservations. That was 2.9. Here, this one. And I can actually even see the command index. These are the commands that I enabled or that I entered. And if I go down here and look at session logs, if I scroll down on S1, you'll now see where I typed in commands on the switches. So be aware that, you know, if you have questions or you get stuck somewhere, I can see it. I can see what you put in. So just be aware of that. And if I don't see a lab listed in the usage and you've turned in a lab, so in other words, you've gone in and turned in one of your labs, but you don't have a corresponding lab in this list of, in the lab usage history list, I'm not going to give you credit for it. You know, the labs are not to be completed in Packet Tracer. They're to be completed in my net labs. It's really the only way I can prove that you're actually using real gear to do your labs. Now, I do suggest if you have real gear in your lab at home, or if you have real gear in your classroom or that you can get to right now, feel free to do some of these labs on your gear in your classroom again or also, because that way you get used to it in your own classroom. But I've got to have this proof that you're actually doing the labs basically just to ensure the class itself, to ensure that we've got you're doing the work, and to ensure that you're learning what you need to learn to be able to pass it on to your students. The other thing I want to do today is I'm going to jump back here and talk a little bit about models, and then I'm going to move forward and look at the physical layer and at the data link layer today. So we're going to look at a couple different things. To begin with, I said we got 6 participants in here now. I'm going to put this up. If you have ever heard of the OSI model before, especially before getting in this class, just click yes. Put a yes in front of your name, or just click on the yes item. So we got some folks here in chat. That's good too. Yep. Yes, Ken did. All right. Anybody else? And you feel free to come off unmute if you want to and discuss your knowledge of the OSI model. And then how about the TCPI model? Many of you seen it before?
Yes, I've seen that one before.
Okay. Yep. I think the key here for you and for your students to understand is we needed a way to describe the communication process between 2 end devices. So in other words, how does the person sitting at the PC on the left, how do they connect to the web server on the right? And how does that communication take place? And how is it facilitated? Now, the weird thing here is that the TCP/IP model is a model that I call a real world model. In other words, when you look at TCP/IP, it is based on the TCP/IP protocol suite. So there's a suite of protocols that are listed here that you have: HTTP, HTTPS, TCP/UDP. The OSI model is a reference model. So it's a model that is based upon, now I will say this, if you've been in networking long enough, you will know there actually used to be an OSI protocol stack, and there still is an OSI protocol stack. No one ever used it. But this is a reference model. In other words, it's trying to show how 2 devices talk to each other. And they did it by breaking the OSI model into 7 different layers, describing what happens to each one of those layers. Now, in the real world, the functions of the application, presentation, and session layers are really pretty much all done by just one layer, the application layer in the TCP/IP model. But the good news about a model is it gives us a way of discussing things. It gives us a reference to discuss the communication process. So if I say, hey, the problem's at layer 3, then you understand that that's a network layer issue, that's probably something to do with IP addressing or something to do with routing, because I mentioned layer 3, which is the 3rd layer of the OSI model. If I say it's a layer 2 issue, then we're looking at the data link layer, which is typically something to do with a network interface card or media access or some other issue dealing with the really kind of the transition from the hardware world of the network interface card to the software world of the network layer. And if I say something's a layer 1 issue, well, it could be it's not plugged in, the cable's wrong, there's that type of issue, because layer 1 deals with everything that is the cabling issues. So it gives us a way to discuss the communication between 2 devices. It also allows vendors, when they're putting their devices or making their devices, to build them for and be able to describe for certain purposes. So if it's a network layer device, and we know it's going to handle routing of logical addresses. If it's a data link layer device, it's going to handle framing. It's also important to know that in this model, the way it works is I describe it to people kind of like the Russian doll analogy, if you've ever seen or know about the Russian doll. So you've got, if I can actually, I got a little miniature here. I'll reach back here. The usefulness of having gaming materials around you. All right, so here is a small miniature. So let me turn off my video here. I'll turn off my, okay. So imagine that we've got this. This is the data that we want to transfer from one PC to another. So this is the web page request or whatever. So I would take this at the application layer, and I'm going to wrap, this is the data, so it's going to be wrapped in that application layer. And I'm going to put an application header in front of it. Sorry, my arms. By the way, good news, I did get good news today. I'm not going to have surgery on my arm. I've got another 8 to 10 weeks of just trying to get it back to where I can even move it, but that's better than surgery. But you take this data, you wrap it up, and you put a header on it. That's the application layer. You pass that down to your presentation layer, put a presentation header on it. Pass that down to the session layer, put a session header on it. But each layer has no idea what's going on at the layer above it. It's just knowing that it's going to provide services to the layer above it and receive services from the layer below it. The only exception to that is the physical layer obviously has nothing it can receive services from because it's the lowest layer of the OSI model. And the application layer has nothing that it can provide services to because it is, well, it actually does provide services to applications, but there's no layer above it. So just imagine that you've got those Russian dolls and you're putting each one inside of one another. And that will help you kind of understand the encapsulation process that is common with the OSI model and with the TCP/IP model. So here are 7 layers. I give you 2 different ways to remember this. If you need to remember layer 7 to layer 1, it's all people seem to need data processing. Okay, so that's layer 7 to layer 1. All people seem to need data processing. If you need to remember it from layer 1 to layer 7, one of my favorites, please do not throw sausage pizza away. Okay, so all people seem to need data processing. There's a mnemonic to help you remember it from 7 to 1. 1 to 7, please do not throw sausage pizza away. Each one of these layers has a specific function. So in the application layer, it provides protocols for communication, for process communications, and I will tell you this provides services to applications above it. The big thing on the presentation layer is many times you'll see it listed as converts data into intermediary formats. You'll also read many places that if encryption or compression are going to occur, they will occur at the presentation layer. It's kind of an old school look at the way these things are. And then session layer is maintains, establishes, and terminates sessions between different services. These top 3 are a little nebulous, folks. That's why in the TCP/IP model, they're all grouped together as just an application layer. The transport layer does provide for typically we say the guaranteed reliable delivery of information unduplicated, in sequence, intact. Okay, and we'll talk about the two different protocols at layer 4 in the TCP/IP model. The network layer is the layer that provides logical addressing. My wife's working from home again today, so she's printing something. Provides logical addressing of logical IP addresses, in our case, is what we're going to be using. The network layer is also associated with routing or path determination. So we're going to determine the path through the network using those logical addresses. The data link layer is framing. This is where we take it and frame it for the appropriate layer 2 protocols that are being used in the network. In our typical networks today, that is the this is Ethernet. So it can be Ethernet, either wireless or wired Ethernet in most cases. The physical layer is our layer 1. I call this the blue collar worker of the networking world. So it's the bit pusher. It's the ones and zeros, folks. It's the light or no light on the link. Now we saw this picture here where the two different models match up to one another. You're going to need to know this. You need to know it for the chapter exam. You're going to need to know it for as you move forward with your studies. I gave you a mnemonic for the OSI model. I have another one for the TCP/IP model. Top down. Top down is ATN or ATN, Application Transport Internet Network. And bottom up is NITA, N-I-T-A, Network Internet Transport Application. So you need to remember that. Okay. Again, they give you a comparison. Again, one of the things I tell you, and I've told you before, if you see things in the curriculum once, it's important. If you see it twice, it's very important. You see it 3 times, it's on the exam. So we've seen it twice so far already, so be aware of that. Any questions on this part of the OSI model, or about the OSI model or the TCP/IP model? Okay, none? All right, well, let's move forward and just look at data encapsulation. Again, going back to my Russian doll example. As we are able to divide messages into different encapsulations, we're going to segment messages. We're going to be able to take and we're going to be able to put messages into smaller chunks. So we're going to segment them so that they're not one big message trying to go across. The reason we do this is so that a single communication won't hog the entire link. It's also so we can multiplex, so we can put different messages on the same line. And the mechanisms of our different protocols will allow us to keep up with how each one of these segments relate to a conversation. And that will be sequencing. So again, we go through here and we break a large communication into smaller pieces. Well, when it gets to the receiving side, all those pieces have to be reassembled. We're going to do that with sequence numbers in the TCP/IP model using TCP sequence numbers. At each layer of the process, the data, again, is being encapsulated as it's going down to be sent across the link. So our request to access a web page, that's our original request, or email data or whatever. It comes in, it has an application header placed on it. That entire information then, by the way, the application header and data becomes data at the presentation layer. And the presentation layer really doesn't even know what's inside of the package that it's carrying. It just knows it puts a header on it and move it down. This is only showing the application layer because it's using the TCP/IP model more than it is the OSI. As you move down, you see there's a transport header with the data. This is called a segment. So if you hear something called a segment, that's the information at that layer, at layer 4 of the OSI model. At the network layer, you'll see that the network header is placed in front of all the information that has come down from the transport, which has the data that's come down from the application. Here we call this a packet. Sometimes you'll see that called a datagram, but In this particular curriculum, they call it a packet, but hey, it's called a datagram on occasion. And then down at the data link layer, you'll see we have a frame header, which, by the way, one of the things you were asked to do, and I think I have, let's see if I got Wireshark on here. Nope, I don't. Let me load up Packet Tracer. One of the things you were asked to do in one of the labs for this particular section was to look and find the MAC addresses or the frame information, the frame header information for a communication. Well, I'm gonna just do a real quick example here. I'm just gonna pull a PC out, pull two PCs out, throw a switch out here. Okay. And let's grab our cables. By the way, here's all of our cables. In one part of the lab, there was a lab that required you to use a fiber optic cable, so be aware there is a fiber cable here. As you drag across each one of these, it will tell you what kind of cable it is. So there is a fiber optic cable if the devices need fiber optic cables. Crossovers straight through. So we're going to take a copper straight through and go from the fast Ethernet here over to just fast Ethernet 01. We'll do the same on this opposite side here. And I will then need to place IP addresses on these real quickly, which again, this is not a, I don't particularly love this. This is one of the way I can always tell students who've had very little experience with real gear, because at the national contest for Skills USA, they had to actually configure real PCs, and they can't configure the real PCs correctly. Okay, so I just put these two on the same network here, and I'm going to go into a command prompt, and I'm going to ping the opposite side. Ping 192.168.12.10, just proving I can ping first. It may take it a second. If not, we'll troubleshoot, but it should start working here in just a second. Come on now. IP config 192.168.10.10. Oh, that's why. You got to put them on the same network. I put this one on 12.10. So you get in a hurry, you make mistakes. So I put this one on 12.10 instead of 10. So this should be 10.11. The problem there was they were not on the same network. The PC0 is on the 10 subnet or 10 network. PC1 was on the 12 network. They will never talk to each other. That is a guarantee. So now let's go to 10.10, and lo and behold, it works. Amazing when you put in the right thing how it will work. So what I'm gonna do now is I'm gonna go to simulation mode, and I'm gonna do a ping between these two. So again, we'll hit up arrow here. You'll see that an ICMP ping goes out. And as I look at the layers here, they will actually show you the layers. So the layer 2 Ethernet header says that the source MAC address is this MAC address. And by the way, I can actually go in here to this PC, and I should be able to go to a command prompt and do an ipconfig/all and see my physical address. So you see my physical address. Oh, they got it backwards. This is going the other way. So this is the source destination, but the physical address is 0. Hold on, I got to open up the right PC. So it's pinging from PC1 to PC0. So if I look here, you will see that the MAC address would be this 0D0BC28.49. Let me go ahead and go forward here, and we'll get this whole communication taken care of. Let's go back to real time. But now I can go over here, and you'll see that if I do an ipconfig/all, you can see that the 00D0BC2848B9 is the MAC address, or the physical address of this PC. Going back again and showing you that you can, under simulation, if we do a ping from here to here, right here's our layer 2 addressing. So this is PC1's MAC address going to PC2's. You also see that the source IP address was 10.11, so this is the source. This is the header information that is added to the devices. In our labs, you're asked to actually use Wireshark, which is a more advanced protocol analyzer, and you can look and find the same information. There, it's called Ethernet 2 header information also, and you'll see the source and destination MAC addresses. And that tells you who's sending, who sourced the frame, and who is the receiver of the frame. As we move forward in our discussions, you'll learn more and more about how framing is used to ensure that only certain individuals or certain PCs see a frame. Okay, we got a question here. All right, what we got here? All right, go ahead, Ken, go ahead. And feel free to unmute if you wanna unmute yourself.
Hey, and it's Ken. I've got it in Packet Tracer, and you kind of answered it a little bit in email for me, but could you kind of sort of give me some hints or some guidance with NetLabs? Because I mean, it is a little bit different with how to actually config, and it just seems it's a little bit, and maybe because it's a little bit more real world in that.
It is. Let me do this. I will start. Wrong thing. I'll start us a lab up. And then, because it takes about 10 minutes, and I'll do that while I'm lecturing, then we'll come back to it. How's that?
Cool.
Yeah, let me go. I'll actually do, let me schedule me a lab here. Let me find our class, and I will do, we'll still do this one. And you're wanting to see how to configure the PCs? Or anything?
Yeah, because that's what we're doing in 7. We're trying, because we're looking for MAC addresses, and I mean, and it's pretty clear in Packet Tracer. But I know I'm missing something, on how to do it, and it'll probably be one of those duh moments when you show us. Okay,
well, I'll start this one up, and we'll look at it here in a moment. Okay, we'll come back to it because, like I said, give it 10 minutes to boot up, and we'll come back. So again, here's our encapsulation. This is an example of showing as it is returning to the client how it's putting an application header on it. So here's the web page itself becomes the data. Then we put a TCP header on it, which we'll learn is source destination ports and protocols. Now here's our IP addressing, and then we'll go to Ethernet. And so when we're looking at Packet Tracer, folks, again, if we look at this particular frame here, or this packet, you'll see it's got layer 3 information. Right here's the source IP address, which is PC1's IP address. Right here's the destination IP address. And here's the neat thing. I can show there's a ping going over. Okay, so that ping goes all the way over to PC0. And then when it comes back, I can actually look at PC0 going back here. I can look now, you'll see that things have been switched a little bit. Because now you've got the, it should be down here. The IP addresses have switched because this is the return ICMP packet. So this, you'll see that the source is now PC0 going back to PC1. And that the MAC addresses have also changed. And so all of this is this information that's being added as we're encapsulating the individual pieces of data. It's also important to note that when it's received on the receiving end, it comes across as 1s and 0s. So here's all of our layer 1 information. And as it comes across, the first thing that the PC does is it takes it and pulls it up and looks and says, okay, this is an Ethernet frame. So one of the first things a PC or a host does is looks and says, is the destination MAC address my MAC address? And remember, all PCs have a MAC address associated with them. So if you do an ipconfig/all, you will see the MAC address on your device. All right. So again, if I go in here and do just an ipconfig/all, you will see it's not called a MAC address on inside of these. It's called a physical address, but that's the same thing because it's the address that is burned into the network interface card on the device. If the MAC address matches the PC that, or the host that just pulled the frame in, it will then take off that header, look and see if the IP address in the next portion matches its IP address. If it does, it will then look at information inside of that header to see what to pass it up to at TCP level. and then it will know what to pass it up to later at the application layer as it continues on through. So what I always tell people that is amazing is it is absolutely amazing that when we go somewhere on the internet, all of these web pages we're going to are being segmented and multiplexed in a process, and everything's being encapsulated on the sending end and de-encapsulated on the receiving end, and it still works, which amazes me considering all the different things that have to go right for our communication to work well. Questions about that, about encapsulation and de-encapsulation? So again, you'll see we've got different addresses. We've got at the physical layer, we just have timing and synchronization bits. This is typically start of frame delimiters, possibility of start of frame sequencing or start of sending frequency and RF signals. At the data link layer, we have our source, destination, and source physical addresses. So these are those MAC addresses. At the network layer, the destination and source logical network addresses are layer 3 addresses. At the transport layer, you're going to learn about as we move forward, you're going to learn about source and destination ports. So for instance, if you connect to a web server, you're connecting to TCP port 80. That's a well-known port. That's what's in the transport layer. And then in the upper layers, there can be other encoded application data depending upon what you're running in terms of the upper layers. It's HTTP, HTTPS, what any of those, it could be, could have other items up in there. But for us, the main areas that we're going to have addresses will be in the data link network and transport layers. Okay. So here again, here's our logical addresses at layer 3. So there's no reason and the reason it's logical, folks, is just like this. There's no reason that I used 192.168.10 other than the fact I just pulled that number. So that has nothing to do physically with the location of the PC or the device. This, however, is a physical address because this MAC address is physically burned into the network interface card. We'll learn more about that as we move forward into the chapter 6, which hopefully you've been reading or have read. Now, here's an important item. Devices on the same network can communicate directly with one another. So in other words, if PC1 wants to connect to and talk to the FTP server, and it's going to put in the destination MAC address, all C's. And now there's a way to get this MAC address we'll learn about later called ARP, which is Address Resolution Protocol. If you have the IP address and you need to know the MAC address, there's a protocol that lets you send out an ARP request and an ARP reply. Okay, we're just going to assume that's already happened. And so PC1 has built a frame that says the destination frame is all C's, the source is all A's, destination IP address is 19, source IP is 110, and at this point, this frame would be sent up to the switch. Now the switch is going to do some things with it that, again, we'll expand on a little bit later when you learn about how switches use their MAC address tables. But it would go out this link here only if the switch had not learned all of the connected MAC addresses. But in a real world, it's going to come in, it's going to go back out this link to the FTP server. The FTP server is going to look at this frame and say, oh, the destination MAC address for this is all C's. That's my MAC address. So it's going to take the data link header off, pull it off, and then look and say, okay, now layer 3 or the network layer, the destination IP address is 1.9. Oh, wait, that's me too. It'll take that off. And by the way, there'll be a pointer at the network layer telling it what layer 4 or what transport layer protocol to send this to, either TCP or UDP, depending upon what was being asked. FTP is a TCP, 20 or 21 would be the 2 ports. So you would have a pointer up to your layer 4 information. So this is how PC1 and the FTP server keep up with their conversation with one another. So on the same IP address or same network, it's sent out to the switch will forward it, and it will be de-encapsulated by the receiving device. The problem comes in when you have this. If you have the device is on the other side of a router, or it's not on the same network. The process that we use, which is called ARP, is a broadcast. So PC1 is trying to get to the device 172.16.1.99, but it cannot send a broadcast across the internet. Broadcasts are bad. Now, that doesn't mean we can get rid of all broadcasts, but we assume and we try to have as few broadcasts on our networks as possible. In this case, PC1 will send out an ARP request that will be flooded out all ports except the one it came in on, and the router will actually see, oh, this PC is trying to get to a remote device. It's 172.16.1.99. The router will then say, okay, I am the MAC address for this remote host because it is the way to get to that remote host. This is called a proxy ARP, or a, what is proxy ARP? So if I go ahead and open up Notepad here real quick. So this process is called proxy ARP, and it's where the local router substitutes its MAC address for the MAC address of a remote host. Then when that frame comes in to be sent, it will go to the switch will forward it over to the router. The router will then look in its routing table, layer 3 table, to see if it has a route to the 172.16.1 network. If it does, it will forward it on through this internetwork. Now, it could be anywhere in the world. But that's the difference between if it's on a local host or a host that's on the same network, the communication goes directly to that host and will come back. If it's on a remote host, it's going to go, the router's going to have to act as a proxy ARP or as an intermediary in order for the PC to be able to connect to that remote web server. As we go forward and you learn more about layer 2, the data link layer, this will make a lot more sense. Okay. So again, here we have it. One thing you're also going to learn is that every single hop along the way here, layer 2 addressing is rewritten. Layer 3 addressing is not normally rewritten. Now, it may be rewritten at R1 because of NAT, but it's not rewritten in our examples here. So, and this here shows you how it's being changed along every way, how the layer 2 addressing is changing as it hops from router to router, because the layer 2 information is changing. So, you know, the source and destination IP addresses don't change, but the layer 2 information does change, because as you move over here, this router is sending something to this router. So the source and destination layer 2 information is the source and destination MAC addresses of these two routers. The IP addresses stay the same so that the receiving router knows where to route this. And then at the end, same thing, you end up with a destination NIC, which is the MAC address of this final web server, and the source NIC will be the router, because it's acting as a proxy ARP for the remote host. Okay, a little confusing, but it's not too bad. I think the big thing here to remember is that this encapsulation process is essential in order for us to be able to get data to move across our networks. Any questions? Okay, I'm not going to spend a lot of time on the physical layer, because the physical layer is pretty easy, folks. I'm just going to kind of blow through this, and let you kind of, the big thing here is know that when you're choosing your physical layer, what you're going to use, you need to think about items such as attenuation. Okay, so what is attenuation? Anyone know what attenuation is?
A loss of signal.
Yep, it's the loss of signal strength as a signal passes through any media or medium. That can be from resistance to a copper cable. It can be from just failing signal strength on an RF signal. So attenuation is the loss of signal strength. Okay, so loss of signal strength, which is normal. I mean, that's not something that is not unexpected. How about crosstalk? Anybody?
The signal from one media bleeds to another, like
Yeah.
copper cable.
Exactly. That's one of the reasons why we call signal overflow from adjacent wires is what I normally say. And it doesn't have to be just from adjacent wires, but I usually say signal overflow from adjacent source. I would just say from an adjacent source. So an adjacent source, whether that be another wire, it could be, you know, a fluorescent light. It could be a power source. This, by the way, is one of the reasons why we look at copper cabling, and we look at the fact that in copper cabling, we have these twists, and you'll see there's a different rate of twist here. You can actually see the different rates in this particular picture. One of the reasons we change the twist rates on unshielded twisted pair and even shielded twisted pair, it's a little hard to see here because they've untwisted it so much. But the reason the twist rates are different in the pairs is so that crosstalk will not be as big an issue. The hope is that by the twist being different, the signals, even if they overflow, won't be in sync with the other wire pairs. Okay, so that's a big thing there. But these attenuation, crosstalk, each one of our types of cables have different levels of this. So when you talk about the last thing we want to talk about is EMI, which is electromagnetic interference. Each one of our different cable types are more or less resistant to EMI. I always tell people the biggest creator of EMI is a nuclear weapon. And, you know, not that you worry about your cables working if a nuclear weapon goes off, but I will tell you that there's an excellent book, if you've never read, that will scare you to death called 1 Second After. I think that's the name of it. But it's actually written by a guy who worked up in one of the schools at Black Mountain. I think it's at Montreat College. And it's about what would happen if a EMP attack took place on the United States. Especially what would happen, you know, a lot of things we don't think about. You know, as soon as we lose refrigeration, if you are a diabetic and it's summer, insulin requires refrigeration. And so, you know, that's, you think about that, not just food supplies, but there's so many different things we have that requires refrigeration or just power to be able to use it. But that's a good one to read if you want to read about basically it's a fictional look at what would happen to society in the event of an EMP attack. But with EMI, when we look at our different types of cable, unshielded twisted pair is probably the least resistant to EMI. Shielded twisted pair becomes a little more resistant. Coaxial cable is somewhat resistant. The one that's completely resistant to EMI is fiber optic cabling because it uses light sources. So the big thing about the physical layer is when you're determining your cable you're going to use in your network, look at the different lengths of runs you need to have. So your attenuation, how long can you run? By the way, unshielded twisted pair, UTP is 100 meters as the max run. And that's 328 feet for the metric challenge. The typical standard though is it's 90 meters for the run, 6 meters for the patch cable to the PC, and 3 meters for the patch cable inside of the data center from the punch down to the switch, which I know is 99 meters, but that's the typical run. What happens if you happen to go past the limits for the cabling in terms of distance and runs? Is it guaranteed not to work?
Errors and retransmissions.
Errors and retransmissions. You also can have a thing called late collisions, which can be a big problem. The biggest thing is you also, especially if you are using unshielded twisted pair, you won't be able to run as high speeds as you would like. So even though the cable may support gigabit speeds, it may not actually run gigabit speeds. The big thing is stay within the limitations of the cable runs and you won't have those issues. The other thing is if you need something secure and you need to run it long distance, use fiber optic cable. Okay. The other thing I always tell people too, and I know wireless is awesome and everybody loves wireless, but personally, if you can put a cable in it, I'm gonna cable it because it's just so much faster and so much more secure. But this is something that's been added into the curriculum, the different types of wireless, 802.11, 802.15, 802.16, which is WiMAX. I saw a thing today, somebody was complaining about they had Starlink, And I will say they had a ping of 618 milliseconds, which is very, very long. They were getting download speeds of 34 megabits per second. They were complaining about it being too slow. And I was like, oh, I'd take 34 megabits per second in a heartbeat. Unfortunately, the launch of the next round of satellites, they've had to scrub it 3 times now. They're on their 3rd scrub. Today it was scrubbed earlier. So any questions on the physical layer? I'm also not going to spend a lot of time on the numbering systems. I think this you can understand yourself. So I do want to jump real quick over to that reservation I had, just so I can show this. Oh, might want to actually go into the reservation. So I'm going to go in here. And one of the things that's important to note is that these are just regular PCs. So if you want to put an IP address on them, this is a Windows 10 box. You just click down here. There's multiple ways you can do it, okay? You could go to Control Panel. Okay, you could go to Control Panel, and you can go to your network settings. Okay, so you go to Network Sharing Center, and you could go there, and you could go to your local, change adapter settings. That's one way to do it. You also can just go down here to the little world here, right-click on it, and go Open Network and Internet Settings, and then go to Change Connection Properties. Hold on a minute. Went the wrong place. Go Ethernet, change adapter options. Okay. So again, open it up, go to Ethernet, change adapter options. You find the correct one we're using here. It says local area connection. Right click on it, go to properties. And then we just go in here and put an IP address on it. So we go to TCP/IP version 4. And instead of letting it do a dynamic address, we give it a static address. So we're going here and just do 192.168.12. I'm remember to use 12 this time, 1210. Tab over, subnet mask is /24. I'm not going to put a default gateway in. The reason being, folks, there's no router in this network. The other thing I want to stress to everyone again, when you're doing the labs, you must use the content from this content tab. You must use this because they are changed for the NetWide Plus environment. So don't use the one inside of the curriculum, use this one. It's imperative you do that. You'll notice on this topology, there's no router, so there's no way or no need for default gateway. So I'm gonna click OK. Just make sure you click OK and OK. Otherwise, when I go down to my command prompt here, it will not actually take place. When I do an IP config, you will now see that my IP address has become 12.10. If I do an IP config /all, you can actually now see my physical address for the Ethernet adapter. So here's my local area connection adapter, and there's the physical address for it. Okay, so that's the MAC address. And one of the things in our next chapter we'll talk about, as you read through it, you'll see that this is a 48-bit address. The first 24 bits are called the organizational unique identifier, and it identifies it as a certain type of device. If we look this up, this would say VMware because it's a virtualized NIC. The second portion is actually the serial number of the individual machine or the individual NIC. This, by the way, was how the BTK killer was caught. He had turned in a manifesto to a newspaper, and the newspaper, he gave it to him in a Word document. Well, the Word document has the MAC address of the machine it was created on in the metadata, or used to, doesn't anymore. And the police were able to actually look at that metadata and track it back to a PC that the BTK killer had used or had access to. Kind of scary there, but so let's go back to PCB. We're going to give it an IP address. I'm going to right click on it. Go to Open Network Settings. Go to my Ethernet. Change adapter settings. Right click here. And I know there's about 30 different ways to get here, folks. There's all kinds of different ways, but this is just one of them. We'll double click TCP/IP version 4. And now I made the other one was 192.168. Can't type, y'all. 12. Yeah, I can't type. 12.11. Because the other one was 12.10. I'm click OK. Click OK. And I'm going to now open up this and ping from PCB to PCA 192.168.12.10, and you'll see that we get the reply. Now I'm gonna actually go a little bit further. I'm gonna do a little bit from another lab. I'm gonna go in here and open up Start Wireshark. Now Wireshark is a protocol analyzer. There's even an entire set of classes you can take to become a Wireshark expert, folks. The Wireshark is a packet capture tool. Do not run it on your networks at school unless you have permission to capture packets, because technically it is a packet capture tool. But what I'm going to do here is I'm going to go in and I'm going to say capture and start. And now it should start capturing. I'll go down here and let's do our ping. And it's not working because we didn't pick the right interface. So it's down here. Let's find the one that's got the actual. Oh, you gotta click the local area connection. So I click local area connection and start capturing there. And now watch what happens when I ping. You're gonna see inside of Wireshark an echo request and echo reply. Now I'm gonna stop this. So let's go in here, pull this down a little bit, and so you can actually see this. So this is the real world version of what Packet Tracer was doing. So here is an ICMP echo request, and you can see this is, if you look down here, here's your source IP address, which is 12.11, which is PCB. The destination is 12.10, which is PCA. We look at our Ethernet, so this is our layer 2 information down here, our framing information. You'll see the source MAC address is the 82FADC, which, by the way, if I go down here and I do an IP config /all, IP config all, you will see that the MAC address here is, in fact, 0050. So source 005056 82 FADC, 82 FADC. So this is showing the initial echo request going from PCB over to PCA. If I go down here and look at the next item, by the way, if I wanted to see just the ICMP stuff, you're also going to apply a filter here. You can put in ICMP, hit enter, and filter, and it will only show ICMP traffic, or should only show ICMP traffic. So apply it. Now you'll only see ICMP traffic. So here's the request. Now here's the reply. You'll notice the reply, actually didn't mean to pull that out, folks. So here's the request from 1211 to 1210. Here's the reply from 1210 to 1211. So this is the reply coming back. So folks, when you actually see on this setup here, we'll go back up and you see this reply from, so the request was sent from 1210, and then the reply came back, excuse me, from 1211 to 1210, the reply came back from 1210. So that's this. And then we send another one. So 1, 2, 3, 4. There were 4 requests, so you should get 4 replies. And that's what this is showing here, that when I pinged it, I got all of that information back. As we dig in here again on the reply, you can see the source address is PCA, the destination is PCB, the source and destination MAC addresses at switch. It's even cool, you can go down here and look, you can even see the ICMP message information. This tells you that this is a type 0 or a ping reply. I go up here as a ping request, it's a type 8, that's a ping request. So this is the actual packet and framing information and everything displayed through this packet capture program. Pretty neat. It's also something that, again, when you do your capture, just make sure when you do it, you go to your interfaces, make sure on your interfaces that you're using the local area network interface. Otherwise, it won't work. Okay, so make sure you're using local area interfaces. So again, I go over here. Let me start up Wireshark on this one. The other thing you'll notice as you're playing with Wireshark is you'll notice that many times you just see traffic or STP traffic or other broadcasts that are taking place on the network, because those that information goes on all the time. So here it is, it's loading everything, loading all the dissectors and all. Find your local interface. Just make sure you double click on local area connection, because that's the one you want to use, and then you can start capturing. You'll see here PBST plus. So this is actually a broadcast coming off of the switch that the PC is seeing because it is a broadcast. In fact, if you look at the Ethernet here, you'll see that it's the source and destination is PBST plus, which is spanning tree, which something we'll go over in our next class. Any questions on this about using Wireshark? This is used extensively in security. A lot of people use it to capture on networks to see what's going on. It's used a lot in network troubleshooting. There's even, like I said, a Wireshark University, so you can go to Wireshark University. La Chapelle is in, but it's there's an entire site and set up for training to learn how to use and get certified in Wireshark. So there's a Wireshark certification, which I'm actually surprised more people don't require, especially in the security world. But it's not a certification that a lot of people have. It's not a certification that you see a whole lot about, but it's an excellent tool, an amazing tool that you can use. Okay. Any questions on this? Please, again, folks, make sure you're using this document. 90% of the class has not been using these documents when they do their labs on NetLabs. And I promise you it won't work, especially when you get to the lab on wired and wireless devices in Module 4 or in Module 4. Okay. Any questions? Oh, okay, we got a question here.
Hey, it's Ken. I got a question and I discovered with Packet Tracer, it'll kind of check off and show, hey, you've completed blank. It'll give you credit, you know. Right. Does NetLabs do anything like that? Because I was looking for it.
No, sir. It will not. That's the thing. Real Gear is not going to do that. So it's we use the packet tracers to give you the basics and help you to understand the commands, and then the NetLabs is applying it. So okay. Yeah, NetLabs has no way to check it off.
All right, sounds good.
Okay. Any other questions? Okay, folks, I'm going to stop here. I'm going to stop the recording.